Okay, so we return now to our workshop with Chrystopher Nehaniv. Chrystopher is from University of Waterloo in Canada, and Chrystopher is going to speak about the axiomatic development of complexity theory for finite groups. Chrystopher, please, you may start. Thank you.
Hey, thank you very much. Thank you for inviting me. It's a very nice opportunity to be able to speak in Ukraine, even if remotely. I want to talk about finite groups, and many people regard, finite groups as largely solved because of the classification of finite simple groups in the 20th century. But these finite simple groups are just the building blocks, the Lego pieces, right? And we want to understand, well, we can build all groups with these Lego pieces, these simple non-abelian groups and the prime order cyclic groups. But we want to understand what's the simplest way in which to build groups, or how complex are different groups and how do they compare to each other. So the idea is to write down axioms for complexity theory for finite groups, and then to just following from the axioms, study what we can deduce and see if there are different functions satisfying these axioms that give us insight into groups. So that's the kind of overall program. And there's a preprint on this from a couple years ago that I posted on Archive, where you can find more details. But I will kind of give you a feeling of some of the broad outline. Yeah. Similar things were done actually in finite semigroup theory, but they surprisingly were not developed for groups. So we're going to study complexity functions. And these are functions from the collection of all finite groups to the natural numbers. And they're going to satisfy some natural complexity axioms. Okay, and you can debate about how natural these are. Some of them I have at the bottom appear quite natural, and one of them, which is quite natural, the embedding axiom, will actually lead into a lot of trouble that would make the theory not very interesting. So actually we won't have that one. But the axioms are things like this. If n is normal in G, so that means that you can build a G from the normal subgroup n and the quotient G mod n, then the complexity of G should be at most the sum of the complexity of those two pieces if we're putting it together. So that's a pretty intuitive one. Here's another one. If you have a homomorphism that maps G onto H, then the complexity of G is at least the complexity of H. And then we have another one, which is a kind of constructibility axiom that says we can build any group from pieces of low complexity. So for any group G, it can be constructed by iterated expansion using some groups B1 through Bn building blocks, each with complexity at most 1. So this is a kind of optimistic axiom that from our fundamental pieces, we should be able to build any group. Okay, and the fundamental pieces mean complexity in particular will be less than or equal to 1. We'll take it'll turn out the simple groups will have complexity 1, but they won't be the only ones. There's a product axiom, and you could have here either equality or less than or equal to. Those turn out to be equivalent. So the product axiom says if G is a product, if you have two groups running in parallel, not interacting, right, just a direct product, then the complexity of G is the maximum of the complexity of the two components. So they don't interact. There's more stuff. It's more expensive if you have the two components, but it's not more complex. Right? That's the intuition of that axiom. And finally, there's an initial condition axiom that says that the trivial group 1 has complexity 0. Okay? Some other axioms that you might want are this one. So embedding axiom, that if you have a subgroup of a group G, its complexity should be no more than the complexity of G. This turns out to lead into trouble, and I'll call that the Michelangelo problem, which we'll see in a minute. On the other hand, this other axiom here doesn't get us into trouble, but it's not needed. It's going to, for the unique maximal complexity function, it's going to follow automatically. So the normal subgroup axiom is that if you have a normal subgroup of G, then the normal subgroup has complexity at most that of G. Okay, so those are our axioms, and we're using actually these 5, okay? And the other 2 are, we'll mark on those later, but only those 5 are needed. The normal one will come out, at least for the maximal complexity function, as a consequence. So do any complexity functions exist? We've written some axioms, but maybe there aren't any that satisfy these axioms. Well, the function that sends, the 0 function that sells all finite groups to the natural numbers, it sends every group to the number 0. If you check, that satisfies these axioms, right? All this is sum, something is greater than other. All these inequalities and equalities say 0 equals 0, or 0 is greater than or equal to 0. So yes, there is a complexity function. The 0 function works. Here's another one. The characteristic function of non-trivial groups satisfies the axiom. So that's what's called delta G is 1 if G is not the identity, the trivial group, otherwise it's 0. Okay, so that actually satisfies the axioms as well. You can check. So they exist, but these 2 are not very interesting so far. Are there any interesting complexity functions? And how are different complexity functions related to each other? So these kind of functions that are mapping finite groups to natural numbers, they're often called arithmetic functions. And we'll be studying complexity functions. So arithmetic measures or arithmetic functions on groups. So you have just some function, oops. Losing my. So you have some function from finite groups, or in group, finite groups to natural numbers. And there are various things you can study, various functions like this, the size, the number of conjugacy classes, and so on. These are all arithmetic functions. We're looking at these complexity functions, which are particular arithmetic functions that satisfy those axioms. Okay, so there's some group theory we're going to need to use. Namely, that for any finite group, there's a unique collection of building blocks, the Jordan-Holder factors J1 through Jk, which are simple groups, and they occur with a specific number of types for every kind of maximal subnormal chain of that group G. So they're the kind of building blocks for the group G. And then there's an embedding theorem, a wonderful embedding theorem that goes back in its roots to Frobenius and Lagrange, but also there's the Kaluzhin and Krasner embedding sometimes. I think I've got these in the wrong alphabetical order. Never mind. So it says if you have a normal subgroup of n of G, then G is isomorphic to an extension of n by G mod n. And in particular, this embeds into a Reith product, a permutational Reith product, where these groups are here acting on themselves. So permutational Reith product means that the groups act on sets. And if you take personal permutational Reith products, that operation of Reith product on permutation groups is associative. Okay, so we don't have to worry about the order in which we take the Reith products, where we put the parentheses, right? So we can embed any group into this permutational Reith product and just look at the group part. Okay. And so moreover, not just the group, but the group acting on itself also embeds in that Reith product as a permutation group. That's fine. And then just some more review elementary group theory. So if you can construct G as an iterated extension of Gi mod Gi plus 1, if you have this kind of subnormal series, and you can embed that into an iterated Reith product. So you can just use induction and that Frobenius, Kaluzhin, Krasner, Lagrange embedding. Okay, and the fact that the Reith product is associative for permutation groups, right? Okay, and then so any given G embeds into a Reith product of its Jordan-Holder factors. The ordering is not unique, but those factors are unique, including multiplicities, up to multiplicities. Okay, so that's called a Frobenius Lagrange coordinatization of G sometimes, right? So that's some background. And we'll use those theorems from group theory to study the complexity axioms. Right. Okay, so let's define now a complexity function. We've seen that the zero function is a complexity function. The characteristic function of the non-trivial groups is a complexity function. Here is an attempt to define another one. So you take all complexity functions, take C, any complexity functions, and then you take the supremum of the values of those complexity functions on a given group, and that defines this complexity function Cx, the complexity of G. Now, it's not obvious yet that that's a natural number, but it is. It's finite because using the extension axiom, you can show that the complexity of G has to be less than the number of Jordan-Holder factors of G, including multiplicities, right? And so you get from this extension axiom applied iteratively that any complexity function has to assign a number that's less than or equal to the number of Jordan-Holder factors. And so this is bounded, so you can actually replace this by a max. So it's not a supremum. The supremum is a maximum. Okay, the maximum value taken.
May I ask you the question? May I ask you?
Yes.
There is the middle axiom about you say that every group can be constructed as an extension of groups of complexity one.
That's an axiom.
Yes, yes. So it prevents multiplying complexity function. So if you have complexity function, just multiply it by some number, then we will get also satisfying all four axioms except for this middle. And so this allows to consider this supremum. Yes.
Yeah. If you multiply the complexity function, say, of a simple group, so that a consequence of that is that all simple groups will have complexity at most one. So that means a multiple of a complexity function won't work if you assign 2 to a simple group or something like that. I think that's what you're asking. So a multiple of a complexity function generally will not be a complexity function because the building blocks have to have complexity at most 1. So we can't double the complexity.
Yes. So that middle axiom prevents multiplying by some numbers.
Yes. Yeah, that's right. You could you could try to define complexity functions instead of I used addition here, and also Rhodes used addition. You could use multiplication. You'll get a different kind of related theory, but that's not been developed. But yeah, you are exactly right. That prevents the multiplying. Okay, so we've seen the existence of complexity functions, right? And so this Cx, this one here, this max of all complexity functions, it is a complexity function. This is several pages of verification, but that Cx does satisfy each of those axioms. So and it turns out to be so it's a maximal complexity function because it obviously dominates, right? So Cx of G is always going to be greater than or equal to C of G for any complexity function. So it's a maximal complexity function. And maximal complexity functions have to be unique. Okay, so this is actually the unique maximal complexity function, because if you had another complexity function that satisfied all the axioms and dominated other complexity functions, it would satisfy this inequality. And so you would get that Cx of G is C prime of G, and so they would be the same function. So that gives you the uniqueness. Yeah. Okay, so there is a unique maximal complexity function, but what is it? And can we compute it? It's not even obvious that this is decidable or effectively computable. It turns out to be. Oh, so this is the problem I referred to earlier, the troublesome problem that goes. This is a quote from Michelangelo. If you look at sculpture, right? If you look at he's a famous sculptor. Vinny works in the Sistine Chapel. He said the sculpture is already complete within the marble block before I start my work. It's already there. I just have to chisel away the superfluous material. Okay, but if you have any complexity function that satisfies this embedding axiom, that the complexity of a subgroup is less than the complexity of the whole group, it suffers from this kind of Michelangelo problem that you can't distinguish these very interesting groups of high complexity. In fact, if you have the embedding axiom added, you will have that the complexity function assigns so I already mentioned that the complexity function assigns a value at most 1 to a simple group, and we can embed any finite group into a simple group. You simply let the group act on itself or act on n elements, and then you take a disjoint isomorphic copy of that. So if you act on n elements here, just make a disjoint isomorphic copy, and then you act in parallel. And so every even permutation becomes an even permutation, but every odd permutation gets doubled and becomes an even permutation. So that means that G embeds in an alternating group, which is simple, right, for n bigger than 2. So you can embed any group into a simple group, which means its complexity is going to be at most 1 because of the fact, right? So that's a problem. So to have a non-trivial complexity theory for all finite groups, we have to exclude the embedding axiom from our list, and it wasn't there. We didn't include it, right? So if you have any, so this Michelangelo problem, as I call it, is if you have any complexity function satisfying also the embedding axiom, that is, if a subgroup has to have complexity less than or equal to the larger group, then that complexity function is at most 1 for all groups. So not interesting. So we avoided that, and then we can actually say, well, what is the complexity function, the maximum complexity function? And this is what it turns out to be. Well, this is a complexity function which turns out to be the maximal one. Okay. So if we take G as a group, and we say mu is the least number of levels in a subnormal chain where the quotients are completely reducible, and I wanted to call it span of gems. The referees don't like that. But that means direct product of simple groups. So if these are our simple groups, these are isomorphic triangles, so-called. These are some simple group, it's another simple group, another simple group. Such a product is a completely reducible group, right? And so G should be, you could take a subnormal series for G so that each of the quotients is of this form. It's a direct product of simple groups. Every quotient is direct product of simple groups. And you take one of these of shortest length. Okay, so G is an iterative extension of M completely reducible groups. Then if that's the shortest such description of G, then of course all the Jordan-Holder factors will appear in these different levels. Exactly the number of times that they appear as Jordan-Holder factors. But the ordering is not unique, and the factors are not unique. But which simple groups and how many times they occur are unique. So this turns out to satisfy the complexity axioms, and it's can be shown to be a maximal complexity function. So it's actually the maximal complexity function, and it has some properties, right? So this maximal, maximal what I'm calling hierarchical complexity, it's less than or equal to the number of Jordan-Holder factors. It satisfies the initial condition. Well, it's checking the overview of checking the axioms. If you have a simple group, it assigns complexity 1, or also if K is a product of simple groups, it assigns complexity 1. You can build any group from iterated extension using groups of this hierarchical complexity at most 1. And then it satisfies the product axiom. It happens to satisfy some other axioms too. It satisfies this quotient axiom, which we didn't include, that the complexity of G mod n is less than or equal to the complexity of G. It satisfies the extension axiom. That is one of our axioms. Okay. Oh, sorry. No, we did include the quotient. The one we didn't include was this normality. So these were the main axioms are all satisfied, but there's also this normality property that if you have a normal subgroup, its complexity assigned by this measure is less than or equal to the complexity of the whole group. Okay. We didn't put that in, but that happens to be a property of this maximal complexity measure. Okay. Let's see. Am I okay?
Okay. May I ask you one more question? What about the definition of mu? Okay, can you show the definition of mu for this previous slide?
This slide.
Yes. So is it true that every finite group has a normal subgroup chain, and so each quotient completely reducible? So every
not normal subgroup chain, subnormal. So a chain in which each subgroup is normal in the one larger, the next one up. It's not a normal subgroup chain; it's a subnormal chain.
Subnormal.
Yeah.
And so it is true for every finite group, we have this property. Yes?
Yes. Yes. Yeah. Yeah. Yeah.
Uh-huh.
You just take you can check actually all subgroup chains and see which ones have that property, and there's always a maximal subgroup, so you can mod out by it, and then and it's using some facts like a minimal subgroup of a finite group is a direct product of simple groups of isomorphic type, and there's a lot of that always exist. Yes.
Okay. So I understand. Thank you. Understand.
Okay, and then so we get that the unique complexity function is this hierarchical complexity. It satisfies the axioms. It's a maximal one, and so it has to be equal to the unique one. And then the corollary of this is that the complexity, this maximal complexity, is effectively computable. You can simply check through all subnormal chains of the group for a shortest one where the quotients are all completely reducible, meaning the quotients are all direct products of simple groups. Right, so there is one. You could take a Jordan-Holder series for the Jordan-Holder chain for the group, and that will be one such thing. So it does always exist, but generally you can eliminate many levels. All right, so I think there are other things that look like complexity functions. There's actually this Sokal length. If you know what a Sokal is, it's the direct product of all minimal normal subgroups of the group. It looks like the complexity function, except it actually, I thought for a long time it is the complexity function. It's completely canonical, and it would give a unique decomposition at complexity, but it's not. It fails one of the axioms. It fails to satisfy the extension axiom, but it satisfies all the other ones. Okay, but so it's always an upper bound for the complexity, the Sokal length. And then we have some upper bounds. If you have the Sokal length or the chief series length or the number of Jordan-Holder factors, those are all upper bounds in this chain for the complexity of the group. Okay, let's see. Am I already out of time? Yeah, okay. Just to mention, so it turns out that groups of every complexity exist. In particular, like this cyclic group has complexity n. The complexity function restricts to solvable groups, and on the solvable groups, it satisfies the embedding axiom or the subgroup axiom, which is so we do get that. We don't have the Michelangelo problem if you restrict to solvable groups. Then I'll stop here. So we get other upper bounds. So for solvable groups, you can make an upper bound like this, which is you take a series with nilpotent factors of minimal length, and then you look at the CeLO P groups, and then you can bound the complexity as the sum of those that come from these nilpotent groups. You can also generalize the complexity function by adding more axioms, saying that nilpotent abelian groups should be complexity at most one, or nilpotent groups should be complexity at most one, or solvable groups should be at complexity most one. And then if you add those axioms, you'll get other maximal complexity functions defined in all groups, and they'll satisfy this series of inequalities. And on solvable groups, these two, this restricts to the fitting height, and this is the derived length of the group. So this generalizes those concepts to all finite groups. And just finally to mention that these axioms that I listed, these 5 here, are independent of each other. For each of them, we have an arithmetic function, Jordan-Holder length, Sokal length, or some other ones that satisfy all 5 except for the one mentioned there in its row. And then we also have functions that fail the subnormal or the embedding axiom, but they satisfy all 5. So these are complexity functions, but they don't satisfy the normal subgroup property or the embedding property. Okay, so sorry, I've gone over time a bit, and thank you all for your attention. I'm happy to discuss with you about this topic further.
Thank you, Chrystopher, very much. Thank you.